Copyright in these lectures is either owned by the ANU or a third party who has licensed the ANU to use it. Students may use the recording for personal study only. No lecture may be communicated online, copied or shared without the prior permission of the ANU.
Last time we did a lot of combinatorics. We found out how to count a lot of things, and I think the most important principle there was you sometimes can't count something directly, so you have to be indirect. Now sometimes that'll mean finding a bijection by which the thing you want to count is replaced by something that's superficially different but is the same in number or easier to count. And sometimes you can't even do it with something that's the same in number. Sometimes you have to overcount, and then you divide. If you've overcounted everything 6 times, say that you divide by 6. Frequently you want unordered ideas, and if you have n objects that can be ordered anyway, we know that there's n factorial ways of doing that. So if you've overcounted by having ordering matters, to make ordering not matter, you divide by that factorial. So that's the potted summary. So now let's go on and back to probability per se, and I want you to recall the axioms of probability, maybe just to check that everyone's on the same page. Can we have some volunteers to tell me one axiom at a time? Anyone? Just speak up. Yeah, every probability of every event is positive. Remember, an event is a subset of the set of outcomes. Yep. Another one? Someone else? I don't mind whether you put up your hand or not, but either way, please speak up so we can all hear. Yep.
Probably the entire sample space has to be 1.
Yeah, the entire sample space has probability 1. By the way, that's the only axiom that actually distinguishes it from the more general concept of a measure. Some people do measure theory in mathematics, and you'll find it's really the underpinning to all of the basis of integration theory and other things. But for us, the whole sample space has probability 1. That's important for independence. So last axiom. Go ahead. You can state it in words or sort of a summary or precisely, I don't mind. Come on, this is the one that actually does everything. The others are kind of no-brainers.
For countable sample points, the union of the sample points, the probability of the union of sample points equals at each.
The sum, yes. Yes. So in case anyone didn't hear, he said that for countably many sample points, the probability of the union is equal to the sum of the probabilities of those sample points. And I'd say it's almost exactly correct. I would use the word event instead of sample point. because events can be more general than sample points. We assume that they are disjoint events, events that don't overlap. That's important because while you could talk about countably many sample points, if your sample points, for instance, are real numbers, it's not possible to get a whole interval by taking a union of countably many sample points. So what it is that whenever you have disjoint events of any type whatsoever, countably many, the union has the sum of the probability of the union is the sum of the probability. Okay, so that's just to get you back in the frame of mind of thinking about probability as an abstract space. So our conclusions will now work for any probability check. Okay, I guess to start with, it's kind of a method, but there are some theorems that will be proven here. Okay, so this is explaining why do we go beyond just combinatorics? Because frequently, firstly, not all outcomes are equally likely. So counting the outcomes isn't so useful if you have to weight them according to how likely they are. Secondly, even if you could count them, sometimes it's too large or too difficult to actually count, but there are other ways to get the answer. So event composition, well, this is not a comprehensive description of the method because it's just something you could try. But sure, try to express your event in terms of simpler events, and then you just have to think about how are you putting the events together. So composition is a kind of a weasel word, meaning any way you could combine events. But we know in set theory there are a lot of combinations you can do. You can do a union of sets, that's A or B. Remember, there is an argument. Some people say that if you do the set A union with the set B, that is sort of A and B. We would never say that. We always say that read this out. You could either say A union B or A or B. And the reason is we interpret the event not because people would say, why would they say A and B? They mean it's all the points in A and all the points in B, and if there was any crossover, then we count those intersection points as well, just once. So that's why someone might use the word A and B. But I just want to proscribe that. I'm not going to say A and B because A and B for us will mean the intersection. Sometimes written without the intersection sign. And that's particularly important when you're reading out probability of. This is the and you think of an event as something happening. Probability that A happens or B happens is the union. A happens and B happens is the intersection. So that's, in case you ever hear and or, that's the only way I'll ever use the word. Now, if I have, neither of these directly gives us, the closest thing we have to a direct way of getting it from unions and intersections is probability of A union B equals probability of A plus probability of B. And in case anyone was wondering, sometimes I write it with a sort of, making a bit of special effort for the capital P. Sometimes I don't, I just write a capital P. I mean the same thing, and the same with the text. So, there's no difference in meaning there. So this needs a proviso. We were just talking about it, yeah? Yeah, you can't see this. Okay. Yep. I just wrote this, but it's not complete because I need a proviso to say probability of A union B equals probability of A plus probability.
Minus the intersection?
Yeah. Okay, yeah. So without the proviso, we would be better to put in minus the intersection. That is the two-set case of the principle of inclusion and exclusion. I was a little bit disappointed to see these notes don't use the word principle of inclusion and exclusion. I think they call them the additive law of probability. That's that's a less standard name for this. I mean, additive could mean anything. I would say countable additivity is just axiom 3. I think a better word for this is inclusion and exclusion, because clearly, you include A, you include B, but then you have to exclude the intersection. That's why it's called inclusion and exclusion. So if you have a union, that's a good way to start. But if you don't know the probability of A or union B, and you don't know the probability of A intersect B, and you don't know independence, which we'll get to in a moment, then you're a bit stuck. Knowing probability of A and probability of B, if you just know those two numbers, this number and that number, what you don't know is how much they overlap. Because if you just know probability of A is 50%, probability of B is 30%, probability of A intersect B could be anywhere between 0 and 30%. Because they could be totally disjoint, in which case the intersection is 0. They could be totally overlapping, or like B could be inside A, and then the intersection of A and B would be B. If B is subsumed within A, B is subsumed within A, then A intersects B equals B. So then the intersection would just have probability of no intersection. And what is a very common thing that people want to talk about is independence. We'll get to that in a moment. In that case, you would multiply probability. But I was just saying that if you don't know they're mutually exclusive and you don't know that they're independent, then just knowing probability of A and probability of B is not enough information to proceed. Okay. So the event composition method. Okay, how would you do this kind of thing? The example is when you're doing die rolls. We know that you can do it. You can write out all 36 outcomes, but you can imagine if there were 5 dice, you wouldn't want to roll out 6 to the power 5 outcomes. Would be insane. So probability that the sum of the numbers is at least 4. Well, yeah, complements can make things easier. So the key thing here is complementation. Sometimes when an event seems to have many, many options, its complement will be simple. So the probability that there are at least 4, A is the complement of B. You're either at least 4 or you're strictly less than 4. And then B is A complement. Right. Remember, complementing is it's called an involution. It's a fancy word sometimes used. It's something that when you do it twice, you get back to where you started. So A is B conjugate, B equals A conjugate. In case anyone hasn't heard that before, I could say complementation is an involution, which is a very fancy way of saying it is its own inverse, right? Because if you do it twice, you get back to where you started. A complement equals B. If you complement A complement, then you just get back to A again. So B complement equals A. So complementation is the key thing here. Now, of course, the probability that it's less than 4 is it could either be 2 or it could be 3. Yeah, because these are the 3 outcomes that lead to getting a total that's less than 3 over 2 dice. Now, as you can see, we haven't really shaken off the sample point method yet because I first took a complement, but then I just wrote out the sample points for the complement. So it's not a big advance so far. Complementation. Getting the probability of getting at least 1 6 on 2 rolls of a die. This is probably, you might think that it's it's easy enough to write that out all 11 cases, but the probability of no 6s on 2 rolls of the die. The key thing is that we'll be using effectively we'll be using independence because you have to get something 1 to 5, 1 to 5, 1 to 6, 1 to... So all possibilities are anything 1 to 6 on the first die, anything 1 to 6 on the second die. And the favourable possibilities are 1 to 5 and 1 to 5. Now this is a special example of independence because I haven't gone through independence in great detail yet. I'm just phrasing it in this sample point-esque fashion. That should come straight back on. Yes. So really, we really want to get beyond counting outcomes, and the best way to get beyond counting outcomes is to talk about conditional probability and independence. I don't know why. These are very related ideas, independence and conditional probability. So, first of all, what is conditional probability? It's saying, it's really given as the key word. You are given that B happens. So you reduce your sample, conceptually what happens is, in your mind, if you're told that B happens, you reduce your sample space to just that subset of the sample space where B happens, which is B itself. Once you've reduced your sample space, there's only a smaller number of outcomes. So the chance that A happens as well, it's A intersects B, right? So just rewriting this with the intersection sign. So A and B have to happen at the same time. There's no, if you're given that B already happens, there's no interest in those outcomes where A happens and B doesn't happen. So it's only the case where A happens and B happens. I have to divide out by probability of B. And the reason that you do this, by the way, this is only well defined, and probability of B is non-zero. So you can't easily condition on an event that has probability 0. And the outcome of that is the probability of, I'll just do dot given B. So if you just for a fixed event B, this is a new function. I just do, instead of probability of event A, full stop, I take a new derived function which is probability of A given B. That's a new function of the event A is a probability function. Once again, on the sample space. I guess you could call that S or omega, I don't mind. So I emphasized at the start when we were getting axioms of probability that a probability function is one that satisfies the axioms of probability. But that's not to say there is only one possible probability function. In fact, the exact opposite is true. There are many probability functions. So if you start with the natural probability function for a particular problem, which we call P, then various conditioned probabilities are also probability functions. And you see why it becomes necessary. I guess, okay, if you really want to check this, we have to check the three axioms of probability. And 1 and 3 are easy to check. Axiom 1 is the probability of A given B greater than or equal to 0. It certainly is, because it's something that's greater than or equal to 0, and then I just divide it by something that is strictly greater than 0. 3 is easy to check. I'll just say you can check it yourself. There is a factor of 1 over probability of B everywhere. Okay, so I'm not going to write out the proofs. People who like proofs can write that out. But you have a factor of 1 over B on the left-hand side and on the right-hand side when you're checking that. And the key thing is number 2. That explains why we have to have the denominator of 1 over the probability of B, because I want the probability of the whole space, sample space omega, intersect B, divided by probability of B. On the one hand, this is by definition this is the probability of the whole space given B. You might think I shouldn't be talking about probability of omega given B because omega is not a subset of B. But it turns out that it's not a requirement that the event should be a subset of B. You just take the intersection. So there's no requirement that it's a subset. So that equals probability of omega intersect B, which is of course B. So that's probability of B divided by probability of B, which equals 1. Okay, so I've checked the three axioms of probability. The bold assertion that I made that the conditional probability is always a new probability function. If you didn't like, you could introduce a new function for Q if you wanted, like Q of A equals P of A given B. But I won't do that here, because this is the totally standard notation for conditional probability. So given an unconditional probability function P, we get a new conditional probability function. And it has the useful feature that this is exactly the way you would update your information when told that B actually did happen, because we discard all the outcomes when B didn't happen. We know that they did. This was also the idea behind Bayesian probability, just how to update your ideas when you observe new information, such as B did or didn't happen. So it's the very, very start of those ideas. So that's conditional probability. I'll even state it as a theorem. This is probably one of the many interpretations here. Probability of A given B is the long-run proportion. This is kind of a theorem stated in colloquial language. Proportion of all experiments. We have to once again assume, to talk about long-run proportions, we have to assume that it is an experiment that can be run again and again and again. So this is a variant of the law of large numbers. Of all experiments, out of those trials, so you don't divide by the total number of experiments, you divide by the ones where B happens. Where B happens, that A also happens. So of the trials that B happens, how often does A also happen? And the also is why you're doing A intersect B. A happens and B happens. So that maybe not exactly the law of large numbers, it's a variant of the law of large numbers. So that's another interpretation. That is this is the third interpretation among the three that are written in the notes. If you write, well, many times, you take of those times where it was more than 3, of those, how many was it even? So, in reality, if I roll a die 6 million times, I expect about 1 million on each number, right? So, more or less, it's going to be pretty close to that. As we know, well, even from first-year statistics, you should remember that the standard deviation of the proportion goes down as 1 over square root n. So the proportions are going to be very close to 1/6 of those 6 millions in each category, 1, 2, 3, 4, 5, 6. So the example was, what's the probability that it's even, given that it's greater than 3? Well, there are 4, 5, and 6 are the numbers that are greater than 3. So about 3 million of the 6 million will be greater than 3. And of those, only 4 and 6 are even. So the probability is 2/3, because about the conditional probability is 2/3. And we don't care about it landing at 2, because we're only conditioning on being greater than 3. So we only care about 2 million are the ones where you get either 4 or 6. And about 3 million would be the ones where you have 4, 5, or 6. So the conditional probability is 2/3. Now, another way to interpret this is if you take you stop at the very first trial where B happens. You repeat your experiment many times. We stop at the exact first time when it is greater than 3. So then, on that first trial, it's equally likely to be 4, 5, or 6, right? So 2/3 of the chance it will be even. So it just goes to show that conditional probability is not always the same as unconditional probability. Out of interest, the conditional probability that, given that it is less than or equal to 3, would be 1/3, because of the numbers 1, 2, and 3, only 2 is even. So it would be 1/3 given that it's less than or equal to 3, and 2/3 given that it's greater than or equal to 3. And in fact, the average of the two conditional probabilities, the average of 1/3 and 2/3, the average of those is 1/2. So the unconditional probability is an average of the conditional probabilities. It turns out that is a general fact that is called the law of total probability. So I'll do that in one second. In that case, it was easy because it was 1/2 times this conditional probability plus 1/2 times the other conditional probability. So the unconditional probability turns out to be, in general, either a weighted or just a standard average of the conditional probability. Now, before I do the law, actually, I think I do, I'm just going to do this slightly out of order. I think the law of total probability is, by the way, this is a proof of the law of total probability, and that is a correct name for it. So, in other words, for A to happen, in our example that was A being even, it can either happen by A happening and B also happening, or A happening and B does not happen. Those are the two ways it can happen. So that's just by disjoint events can have their probabilities added. And then we go on to say, that a probability of a product, of an intersection, it's always good to remember that you can do an intersection using conditional probabilities, just by the definition of conditional probability. So that's equal to the probability of B times the probability of A given B. If you're wondering where that came from, I just cross multiplied it. So that's always worth remembering. And I should really, just remember that if probability of B is not 0, you should really assume that probability of B is non-zero to have this concluded. Because if it's not, you're multiplying by an undefined quantity. That's an undefined quantity. The probability of B is 0. And equivalently, you can do it the other way around. Probability of A intersects B, of course that's symmetrical, is also probability of A times probability of B given A. If probability of A, probability of B given A, if probability of A is non-zero. So both of those are worth bearing in mind. Law of total probability just puts it together with B and B complement, because those are the we say that B and B complement are a very fancy way to say this would be that they are mutually exclusive and exhaustive events. We know what mutually exclusive means. That's the same as this drawing. Does anyone know what the word exhaustive means? If I do an exhaustive search, what is that?
The probability for one.
Yeah, an exhaustive search would be to search absolutely everywhere that it could possibly be. So an exhaustive pair of events are events that exhaust the whole sample space. So precisely, exhaustive doesn't mean anything about probabilities. It's just about the event. B union B complement equals the whole sample space, which I've been calling omega, and the set of notes has been calling S. I don't mind which of those two notices. The whole sample space. So whenever you have mutually exclusive and exhaustive events, the law of total probability holds, because it's essentially taken. There's a good picture. I think it's even in the notes. Yeah. Okay. Here's the picture of. Oh, I was claiming that this was the proof of the law of total probability. It pretty much is, but the notes write it out in a bit more gory detail. But essentially, if A is the circle, you can see B and B complement are the mutually exclusive and exhaustive events. Okay. They exhaust the whole space. That's why they're written as just a breaking up of the space. And I want to, so. It's funny that there's no intrinsic reason why we should be restricting to only two events. Okay, yeah, that's the concept of partition of an event. So you'll forgive me, I'm skipping around in the notes a little bit because I just want to get things done quickly. There's nothing essentially different between the law of total probability for two exhaustive events. Your two exhaustive events are B and B complement. If you think about it, if you have two events that don't overlap and they exhaust the space, one of them is B, the other has to be B complement because they're exhausted. They cover everything and there's no overlap. So two mutually exclusive and exhaustive events are just B and B complement. In general, if you have mutually, so another way to say that would be B1 up to Bn, just another language for the same thing, are mutually exclusive and exhaustive events. That's often how I well, actually, that's slightly partition of an event. Yeah, I'm just going to change these. No, of course, a partition of an event B would be a partition, right into the union of disjoint events. But we don't care about partitioning any event other than the whole sample space. So union is S. So in that case, I'll say they're mutually exclusive and exhaustive events. So then their intersections, pairwise intersections are 0, and the union of all of them is S, the whole sample space. So I'm just going to wipe S. So C, D, and E form a partition. Okay, so in this context, C, D, and E form a partition of B. Yeah, but I don't know. You can sort of ignore that. It's not so important. So the key thing is law of total probability for several events. So if B1 up to Bn, so the same thing, they are mutually exclusive and exhaustive events. Okay. So the key thing is that you can then, if you have then some unrelated event A, you can ask, how did A happen? There are effectively n different ways A could have happened. A could have happened and B1 also, or A could have happened and B2 also, or etc. A could have happened and Bn also. Because at least one of the BIs has to happen. Not at least one. Exactly one of the BIs has to happen. That's the whole point of it. Mutually exclusive and exhaustive events are just like choices. You have to make exactly one choice. Exactly one of the BIs is true. So that means when A happens, it must have happened through A and exactly one of the BIs. So I add them all up as exhaustive events. Then I can write them using conditional probability. Say, first of all, what's the chance that B1 happened, and what's the chance that A happened given that? Plus, chance that Bn happened and A given that. Add them all up. So I won't go through that event in The law of total probability is the same in either case. Now what we're going to do is independence, because for me this is the key, really the key idea in all of probability. Unfortunately, you can't always have independent events, but we often want to get as close to independence as we can, because that allows us to make very powerful mathematical conclusions. Events are independent if the probability of the intersection, remember that's A intersect B, is equal to the product of probability of A times probability of B. Sometimes we write A is independent of B. It's a matter of taste, and different books will do different things. I like to use a double-barreled independent sign, because often that's used for perpendicular in Euclidean space, which is a slightly different concept. So sometimes related, but a different concept. So I often like to write it like that. And we write, dependent means not independent. But independence is the key concept. Okay. It can be shown that. Well, it's very easy to check that, because remember, chance of A given B is chance of the intersection divided by chance of B. So if you just cross multiply this, chance of A intersects B divided by chance of B equals chance of A. You can see that that's all that's being stated here. That's exactly the same as this definition of independence. There's a slight, and I said it's exactly the same, there's a slight asterisk, so I'm saying it's exactly the same. What's the slight difference between those two? Anyone who's a bit pedantic or careful about edge cases? Yeah, being zero. I didn't hear very well. So if you are going to say something, please say it pretty loud. People talk about probability of being zero, in which case this can't be defined. Yeah. So the point is independence doesn't require that. So if not only the empty set, but if any event has probability zero, then E is independent of all other events. Okay. E is independent of, a probability zero event is independent of every other event. The reason is, on the right-hand side, you would have zero times something. On the left-hand side, you would have, E, you use monotonicity of this, because if probability of E is zero, then something, an even smaller set must also have probability of zero. So if that happens, then you have zero equals zero. So it's certainly true that any event with probability zero, and certainly the empty event, is independent of all other events. Even more is true. Possibly the independence have, and another, I'll even call it a proposition because it's easy enough to prove, is that if A is independent of B, then the same is true if you tried to take complement. So A complement is independent of B. And remember, independence conceptually is a bit about information. Does the information in A tell you anything about information in B? No, it doesn't. They're independent. So knowing whether A happens is the same as knowing whether A complement happens. And A complement intersects B is independent of B complement, and A is independent of B complement. So all the four different ways that you could turn that around are true. And let's, does anyone, I know I'm overriding the example too much, but the proof of that, how am I to prove, okay, it's easy enough to get from here to here. If I can do from here to here, then the other steps are the same as with B instead of A. So really I'll just do proof of this first step. We're given that A is independent of B, so probability of A intersects B is equal to probability of A times probability of B. That's what we're given. Okay? And I have to say something about, this is what was given because this is the hypothesis in the proposition. So then we have to prove something about probability of A complement time intersect complement B plus probability of AB. We have to use this fact somehow. Can anyone remember the law of total probability? If I say A complement B plus AB, yep. Yeah, exactly. These are just the two different ways that B could have happened, with A or with A complement. But on the left-hand side, that left-hand side is equal to probability of A complement B plus probability of A probability of B. Okay, so probability of A complement B equals, move everything onto the right-hand side, probability of B minus probability of A times probability of B. So I'll take that as a common factor. Probability of B, 1 minus probability of A. Now, can anyone recall what 1 minus probability of A is? Yeah. Complements have complementary probabilities, which means the probabilities add up to 1. So probability of A complement is 1 minus probability of A. So that's the end of the proof. There's a lot of little propositions that you can prove like that. So the key thing about independence is the information. By the way, this characterization of independence, even though it doesn't account for the case where B is 0, probability of B is 0, it doesn't account for that case. But it's more intuitive because this says that there's a probability of A happening. That probability doesn't change if I give you new information about B. So knowing B gives no new information about A. That is what it means for events to be independent. Knowing that one event happens gives no new information about the probability of the other event. And same, it's symmetrical. Knowing that A happens gives no new information about the probability of B. So that would be this variation. They're both true. But we like this way because it accounts for the probability 0 case. Also true if, I'll just say under this note, if probability of E equals 1. I mean, I gave a little reasoning for why probability of E being 0 means it's independent of all other events. Can anyone say what leads me to extend that also to events of probability 1? I said that any event, certainly the whole sample space, that any event of probability 1 is independent of all other events. Can anyone kind of see a proof? It's hard to see, but it is kind of hiding here on the page for us because it's a combination of if E has probability 1, then E complement has probability 0. A probability 1 thing is just the complement of probability 0 thing and vice versa. So E complement is independent of everything. Now, if E complement is independent of everything, that means that E is independent of everything. That's this proposition. So remember, independence is about information. Knowing whether E happens or not gives you no information about other events. So knowing whether E complement happens or not also gives you no information about other events. That kind of makes sense because if something effectively never happens, the probability is 0, it doesn't give you any more information about other things. And if something effectively always happens, it doesn't give you any more information about other things. We're going to move on from independence. The multiplicative law of probability. Is that even a thing? Okay. This is another way of writing the conditional probability. I think that's a grandiose name for... Conditional probability, of course, is this ratio, but if the conditional probability exists, you can just write the intersection as probability of A and probability of B given A. And of course, the order of that does not matter, but probability of B, probability of A given B. But the proviso here, probability of A non-zero, is quite important, because you might think you can still write that, but it's not. It's 0 times something that's undefined. So that's not a good multiplication. And once again, for this to be true, you want probability of B to be non-zero. It's kind of poor form not to put the provisos there. Okay, white card drawn first and then a black card. By the way, these are independent. When you talk about... I said, sorry, I take that back. They're not independent because once you've taken out the first card, the second card then has one fewer cards to choose from. So when you take sampling without replacement, they're no longer independent. When you sample with replacement, every trial is independent. Okay, well, the white card being drawn first, of course, there's 5/8, and a black card is drawn second. You have to say that given that a white card was drawn first, the black card second would be 3 out of 7. It would be 3 out of 8 if it had been different, if a black card had been... no, it would be 2 out of 7 if a case where the conditioning won't make a difference is if they were independent, but these are not independent. Okay, that's law of total probability. There's a slightly technical proof of that. Let's just do this example. I know it's been written out. Probability, so the two events are cloudy tonight and rain tomorrow. So rain given cloudy is 0.7. Probability of rain given not cloudy is 0.4. Probability of cloudy, so this is just law of total probability, is 0.2. So probability of rain, you just do cloudy, rain given cloudy, plus not cloudy. You just think of the two different ways it can happen, rain given not cloudy. Okay, so 0.2 times 0.7 plus 0.8 times 0.4. What's that? So, okay, 0.46. Venn diagrams, additive law of probability. I really don't like the name. I'm going to call it inclusion, exclusion. Or the principle of inclusion and exclusion, if you're being fancy. Okay. But that's n equals 2. Inclusion, exclusion is true for any number of events, and I gave you the formula for that. So, yeah. By the way, these are not independent. Being cloudy and rainy are not independent. As you imagine, cloudy makes it much more likely to be rainy. So when you want to find unions, you'd better substitute in you have to use a special, I guess it was called the multiplicative law of probability to find the probability of the intersection. And then you just add up these two, you have to find the law of total probability to find probability of R. Okay, so 0.2 is the chance of cloudy, 0.46 is the chance of being rainy, and then you subtract the intersection. By the way, probability of cloudy and rainy is, that's just 0.2 times 0.7. So that was one of these two terms. So another way, effectively we've added on both the terms, 0.2 times 0.7 and 0.8 times 0.4, and then we've just subtracted off the 0.2 times 0.7 term again. So there was a bit of redundant effort there, but that's one perfectly fine way to do it. Now Bayes' rule is the main way that we update probabilities with new information. So Bayes' rule said that it's also sometimes conceived as a way of relating probability of B given A to probability of A given B. And that's an important concept because it's naively possible to assume they're the same. But the classic example people talk about is discussion of tests for diseases. It's a very common one because you have very small probabilities of actually having the disease frequently. So you might think a disease with a sensitivity, a test with a sensitivity of 95% is 95% likely to tell you that you have a disease if you actually do have it. So then you get your test and you test positive, and you think, oh no, I'm 95% likely to have the disease, and that's actually totally false. It's often much less than that. So I think there's probably an example. But the main thing to bear in mind is probability of B given A. Probability of disease positive given test positive is often totally different from probability of test positive given disease positive. And in fact, there's a factor that relates it to probability of B divided by probability of A. By the way, this first way of writing Bayes' law is very easy to see because probability of A, probability of B given A, that's nothing other than I guess they call it multiplicative law of probability. That's the chance that they both happen, right? So on the one hand, you're doing it in that order, A first, then B given A. In the other hand, you're doing it that order, B first, then A given B, and they're exactly the same. So that's a proof of this first form of Bayes' rule. So there wasn't much to prove there. And then to go from here to here, we use what was called the law of total probability. Okay. That's simply how you go from there to there. So, and the key thing is you can find probabilities given A when you didn't have any probabilities given A to start with. You just have to add up a whole lot of other things. And the best way to think about this is there are two ways that B and A could both happen. There are two ways that B could happen. One is by B happening with A also happening. And one is by that's just explaining how does A happen overall, but this is the denominator. How many ways can A happen? Well, it could happen that A happens with B also happening, or it could happen that A happens with B not happening, and those are the two things on the bottom. Now, of those two ways of happening, we only want the former on the numerator. The numerator should be the probability of B and A both happening. That should happen when B happens and A also happens. So of all the common principle with Bayes' rule is of all the terms you have at the denominator, exactly one of them appears in the numerator. So this should, generalizations to several events, because this is exactly the same. I'm going to point to that. Bayes' rule for several events. Suppose that B1 up to B in form of partition events. So this is our famous word, mutually exclusive and exhaustive. So then the chance of a particular one of those exhaustive events happening given A. On the numerator, you want them both to happen. So probability of BI, probability of A given BI. That's the way that we get BI and A both happening. On the denominator, because it's given A, on the denominator you want probability of A. So that means you want all the different ways that A could happen, which is A happening with B1, or A happening with B2, or A happening with Bn. Because exactly one of the BIs happens. That's mutually exclusive and exhaustive. There's exactly one of these BIs that's true. So these are all the different ways that A could happen. And we want to single out of all those different ways that it could happen, we want to single out the way that also includes BI happen. So that's the ith term of the denominator is exactly the one that appears on the numerator in Bayes' rule for multiple events. Okay? So it follows from the law of total probability for several events. By the way, this is inclusion, exclusion. We've done this before. There's some discussion about this in the tutorials. Don't check by a sample point method. Now, there's a little digression about the number of permutations that don't leave anything in their original position. Spoiler, it's approximately 1 over e. In the natural logarithm base, 2.718281828. I like to say that because it sounds like it's a rational number, but it's not. It only repeats 1828 twice, not forever. Anyway, at 1 over e, that's roughly how many of the permutations actually leave everything in place. So the final thing I wanted to emphasize before we end today, as you see, there's a lot of examples here, and I'm not going through all of them. The law of total probability is the same, regardless of whether it's just 2 events or n events. The principle is the same. The one thing that changes a little bit with several events is pairwise independence. I just want to say that this is useless. Okay, but it's important to, you might think, when I say that n events are kind of independent, I want you always to think about mutual independence. This is the useful reason. And the key thing is, it's not enough for 3 events to be independent. It's not enough that the probability A intersect B intersect C is the product of all 3. It also has to be true for all subsets. Now, why do we say that? Because for independence to be useful, we want that no combination of any of the events gives you any information about the other events. It's possible to have this funny thing where you have a coin which has either heads or tails, a second coin which has either heads or tails, independent, and then a third coin, I'll just say this is x and this is y. I'll just say your third coin z equals x plus y mod 2. So the exact details of this don't know. Essentially, z will be heads if x and y are the same, and tails if x and y are different. So, and then you've got 3 events. X equals heads is independent of y equals heads. That's by definition. It's easy to check from the definition that x equals heads is independent of z equals heads, and y equals heads is also independent of z equals heads. So this is pairwise independence, and it's a useless concept because it does not imply that x, y, and z are all independent. It does not imply that. And in fact, you know they're not all independent because the information of x and y together tells you z without a doubt. To be independent, knowing x and y shouldn't give you any information about z. But here I constructed this artificial example where knowing x and y together gives you the exact value of z. But if you only know x, then z